Hello everyone. So the last video we saw how to calculate the present value of an annuity. Now let's look at the future value of an annuity. So we have an example where I invest say $500 at the end of every year for the next 5 years when the interest is compounded at 10% annually. Now what is going to be the amount in my account at the end of 5 years? So I'm making repeated investments every year. So before all of that, so this question may initially seem very similar to what we've done in terms of understanding compound interest, whether and the typical formula. I put $1,000 in my account at 8%. What's the value at the end of 10 years, and so on. It's very similar to that. But the key difference that you have to notice here is instead of making a one-time payment at the start of the term and just waiting for it to grow over a given time period and get the final amount at the end of the time period, in the case of an annuity, we're going to be making these payments at regular intervals. I'm going to be making $500 investment at the end of every period. Right? And therefore, in order to find the future value of all of these individual payments made over a period of time, it's going to take a little bit more calculation to figure out what the future value would be. Now let's use this example and try and understand how to calculate the amount in the account at the end of all of these 5 years. So we have a timeline drawn here where there are 5 years and I make $500 payment at the end of each year. Now let's take the case of the first $500 that I pay at the end of the first year. So at the end of this year, I deposit this money. And now, given that my annuity is for a period of 5 years, this $500 is just going to sit in the account for the next 4 years until the 5 years elapses, right? Because I'm making this payment only at the end of the time period. So the 500 is going to sit in the account for 4 years and it's going to grow at the rate of 10%. It's going to compound at 10% every year. So this money at the end of the time period is now going to be 500 into 1 plus 0.1 to the power 4. Right? Similarly, this second installment of money that I'm putting in, the second $500, is now going to sit in the account for the next 3 years. Remember, I'm putting in this money at the end of year 2. So we have 3 more years before the entire time frame of the annuity is over. So this 500 will spend 3 years in the bank and it will grow, it will compound over those 3 years. So at the end, this money is going to be 500 times 1.1 to the power 3. Similarly, the third installment is going to sit in the account for 2 years. So it will grow to 500 times 1.1 squared. The fourth installment will sit just for 1 year and it will grow from 500 to 500 times 1.1. The final installment, which is made at the end of the 5th period, is made at the time when the annuity itself is ending. So it's not going to stay in the account for enough time for it to be able to grow. So when this 5th installment at the end of the 5th year is just equal to the actual value of the installment, which is just 500. So if I sum up all of these numbers, that is going to give me the amount. That is going to give me the answer for the total amount that is in my account at the end of the 5-year time period. So let me add this up. And that is what is called the future value of an annuity, where I make annual or where I make periodic payments of equal amount. And if I sum up, if I want to find out the final amount that's in my account or the final future value of this annuity, this is the process by which we arrive at this number. So we have 500 plus 500 times 1.1 times 1.1 squared plus 1.1 cube plus 500 times 1.1 power 4. If you notice, this is a finite geometric series, so I will encourage you to go and plug in the numbers and calculate what the future value comes to be. And that's an exercise left to you. But what I want to now do is generalize this principle that we just saw. So instead of $500, if I say I invest $8 in an account for n periods, and R is going to be compounded at each period, and the amount is going to be compounded at the rate R for each period, what is going to be the future value of all of these payments? what's going to be the final amount that's in the account at the end of these periods? Let's figure out. So the amount A that I put in the first time period, that is going to remain in the account for another n minus 1 periods, right? One period has elapsed. There are n minus 1 more periods to go until the end of the annuity. And until the end of the annuity, this amount is going to grow. So the final value of this A invested in year 1 is going to be A into 1 plus R power n minus 1. Because it's going to grow over n minus 1 periods. Similarly, the amount A in the second year will grow over n minus 2 periods. Okay, this n minus 2 is nothing but the total time frame minus the amount of time that has elapsed. So in the remaining time will be the amount of time that this money A will stay in the account, and so it will have the opportunity to grow over that time period. So you have A times 1 plus R over n minus 2. And then the third period will have A by it will have n minus 3 periods to grow. So you end up having A times 1 plus R over n minus 3 and so on. So when you get to say the payment that's made at time n minus 3, well, it's going to have n minus 3 periods to grow, whatever is left to grow. And then this will have n minus 2 periods to grow. This will have n minus 1 periods to grow. The last is just going to be what it is. Or in other words, 1 plus R over n minus n. It doesn't have any more periods left to grow, so it's just going to be the same amount. And now when you sum up all of these numbers, you get the future value of an annuity. And that's nothing but A plus A times 1 plus R. So if you see this second number, right? A 1 plus R raised to n minus 1 is nothing but just 1 plus R. 1 plus R raised to n minus 2 is just 1 plus R squared, and so on. So that's what I'm writing down here. And so on to A into 1 plus R over n minus 1. Now this is very similar to the sum of a finite geometric series, where you have A times k power n minus 1 by k minus 1, where A is the first term of the series, which happens to be A in our case as well. K is the factor by which you multiply each number to get the next one, and that is 1 plus R. So plugging in these values here, the future value of annuity is just going to be A into 1 plus R over n minus 1 by 1 plus R minus 1. It just becomes A by R times 1 plus R over n minus 1. And that is the future value of the annuity. Okay, so now we have so far derived the formula to calculate both the present and future values of annuity, and I hopefully I've hopefully given you the intuition behind how these expressions end up getting calculated. Now, very quickly, we'll see an example where we're asked to calculate the present and future values of a deposit of $1,000 in each of the coming 8 years at a given interest rate. Now, how do you know this is a question that pertains to annuity? The key phrase here is each. So there's a deposit of $1,000 in each of the coming 8 years at a rate of 6%. And so that's the clue that you need to know that you're working in an annuity problem. And the question asks us to find the present and future values of an annuity. And given the values of A, N, and R, which we can gauge from the problem, then it's just the straightforward next step is to just plug these values into your formula and get an answer. And so the present value of the A comes out to be about 6,209.79. And the future value of this annuity is about 9897.47. So look at the future value, even though we're putting in $1,000 per year for 8 years, we're doing this deposit every year. So every deposit is going to grow over a particular time frame. The first deposit will go for 7 years, second for 6 years, third for 5 years, and so on. And so when you add up the final amount, then you end up getting $9,897, which is, I think, pretty good. Now, the last part that I want to go over in this video is, we saw that annuity is one where there is a fixed time period. It ends at time n. Well, if it doesn't end but just keeps going on forever, if n goes to infinity, then the annuity becomes a perpetual deal, so it's a perpetuity. Now, how do you find the present value for perpetuity? Well, you start off with the same expression that we did to calculate the present value of an annuity, except that now the series doesn't stop at the nth term, but it goes on forever. And this is an infinite geometric series where the first term is either 1 plus r, the ratio or k is given by 1 by 1 plus r, and now r is a positive number, so 1 by 1 plus r is a fraction. So your k falls within the absolute value of k is less than 1. So we can plug these into the formula to calculate the sum of an infinite geometric series where absolute value of k is less than 1. And when I plug in these values, I get a very simple expression to calculate the present value of perpetuity, just a by r. So, and I have a question, a sample example, where we're asked to find the present value of a series of deposits. So you're making deposits every time period at the end of each year, and this goes on forever in perpetuity, and we're given that the interest rate is 14%. So, and we're asked to find the present value of the series. Well, we know how to calculate that because we have a formula. So plug in the numbers. So you just have to do a by r, 1000 by 0.14, and that gives us about $7,000. So that broadly brings to a close what I wanted to do on annuities. In the next video, I'll do a simple example that applies the principle of annuities in dealing with mortgages. So I will see you in that video.